Hello, guys. Today's topic is actually an interesting one and is one that's come out of curiosity. And from the title, a lot of you have probably clicked on it. I'm very interested to hear what this topic is going to be about. Let me set the scene here, give some context. So, in the market today, there are a bunch of database providers and both specialized and general purpose database. When I engage with developers that are building this Gen AI products or AI applications, one thing they're always asking is, what database should I be using? Or even generally, what components should I be making my AI stack of? And there are a few databases that we know that some developers are very used to. And one of them is Postgres. Postgres is a widely used database and it's existed for a very long time. And it's used in a number of applications today. And with the PG vector extension, you can actually store vector data on Postgres. So that's what today is going to be about. Today is going to be about talking about AI workload, the key things that matter about AI workloads, and looking at how MongoDB and Postgres with the PG vector extension handle this top of mind consideration for developers. So I'm going to get straight into the code. Normally, when we are here, there's a presentation, but I want to just start off and because we are going to have a lot to talk about. And I'm just as curious as you, exploring this different database systems, exploring different ways to implement AI, Gen AI application, exploring different techniques. So this notebook I'm going to present to you is actually available on the Gen AI showcase repo. And I'm telling you this, and we put it out there because we want you all to get this notebook and maybe tweak it and provide some PRs and provide some insights as to how you would optimize any of the configurations here. On that note, I will start off with the general purpose of this notebook, which is really the vector database comparison for AI workloads. And what I mean by AI workloads, generally, I'm looking at any application that is implementing features of AI or maybe today generative AI. So they require certain stack compositions, certain database requirements, certain library requirements. You look at the AI stack, there are tools specifically created and geared towards AI workloads. Today, we're going to be looking at a typical data set that we expect to see when dealing with AI workload. This data set is sourced from Cohere and hosted on Hugging Face. It's the Wikipedia data set. It contains vector embeddings, contains some data, but we're also going to generate our JSON data, and which is a data structure that is common when you're dealing with AI workloads. So normally I like to start at the end. So let me show you where we're going to get to, and then I can explain how we got there. The two areas of an AI workload I'm going to be focusing on for this discussion, and is a discussion because I want you to put in some comments, ask questions, and let's increase our collective intelligence. So I'm going to be thinking about a typical AI pipeline or even a RAG pipeline, which is very common. And there are two processes that are very top of mind for developers, which is the ingestion process, which is the act of getting data from various sources and putting it into a database, and then also a retrieval process. So those two process are very important when you're building most of the applications we see today that constitute for AI workload. And the two databases we're going to be comparing are is MongoDB, obviously, and then Postgres with the PG vector extension. The criteria I'll be observing are the insertion time. And what I mean by insertion time is how quickly can we take data and store it within these databases. And we're going to be doing this storing of data in different batch sizes. And this is reflective of what we expect or what we see in production environment and in most POCs and production application is where we see different batch sizes representing different rows of data being ingested at the same time into a database. So very quickly, we can talk about the results, but high level is Postgres is able to ingest data at a decent rate. But when we come to MongoDB and when we start to actually look at that scale and scale up MongoDB and scale up our AI workload, we start to realize that MongoDB remains performant. And there are some spikes here we can see, and I'll explain that, which is I ran this benchmark test on my local machine on my laptop. The configuration for this test are on the top of this repository. We'll go through it later, but you can also run this as well. And I'm running single local instances of both Postgres and MongoDB, single nodes, and I've allocated the same compute resources and storage resources to both databases. So I've done no optimization on the MongoDB side. Maybe tweak some parameters here, and we'll talk about them on the Postgres side. There are some parameters we have to tweak, but I'll point them out as well. But here we can see inserting data into MongoDB is very performant. And when you start to scale, we start to see the performance being maintained. But in comparison, we have Postgres having some increased insertion time as you start to go up to, this is going to be a 40,960 record. Within this notebook, we're using a data set from Cohere. It contains 35 million records. That's going to be a lot to get through, but I'm taking a subset of that and just about 100,000. So this numbers add up to 100,000. We're ingesting 100,000 data points into our database in different batch sizes. The next item I want to highlight is the retrieval metrics as well. So this is the part where I hope this is not too small. Let me see if I can zoom in. And that is, I think that should be fine. When we look at the retrieval component, these are the things that are top of mind for developers building this AI application. How fast can I make a query to the database and get some documents, some answers, some context back? And this is one thing that is top of mind, especially as we go into 2025, when one of the biggest trends that we see that is going to be coming is conversational AI. And latency is very, very important when we're talking about conversational AI. And what I mean by latency is request for data to get in the data. That time is what we're measuring as latency. And when you look at this diagram, what we're looking at is the key thing is the lower, the better. And you might notice a spike here. Most databases need a warm-up period. I've not kept a warm-up function here for both of the databases, but we can imagine this is the warm-up for both of the database. And you can see that both Postgres and MongoDB has this spike. So MongoDB is in green and Postgres is in blue. But as we start to scale, we start to see that MongoDB remains performant as we go into typical sizes of AI workload. And in the x-axis, what we have here are concurrent queries. And what this is we're actually sending queries to the database at the same time. So here we have 16 queries to the database at the same time. I will show you how this notebook is structured, what the queries are composed of, and even the data set. So the average latency, how quickly can I get my results back? Very important for AI applications, for Gen AI applications that are looking to be consumer facing, even enterprise application. And as we go into 2025, looking at conversational AI, latency is going to be top of mind for a lot of developers. The next item I want to actually cover is the throughput. This is the amount of queries per second that the database can handle. So what we can see is as we start to scale and start to increase the amount of queries we're putting to each of this database, we see that MongoDB again remains performant as we go into the realm of scale, which is where you want to be thinking, or where you want to be at, scalability. So again, performance in the throughput. And the last thing, again, is latency, is the P95 latency, which is a metric that measures the amount of time it takes for you to get 95% of your results back from your database. You can put this down to P90 and do different measurements around here. So again, this is the warm up for the spike, but as we start to look at the real scenarios, MongoDB remains performant as we scale. And this spike here, I'm not running this in a clean virtual environment. Maybe that's one we did in a video, or even one with in a cloud environment. That's an environment for another video. This is on my local machine. All the configuration listed at the top. So those are the areas where we want to focus today. And like I said, I want it to be a conversation because there are different things we can do to both of these databases to improve the performance. But one thing I want to get very earlier on is when I'm speaking to developers that are building this application, one thing that is top of mind is developer productivity. Time to market is a competitive advantage for a lot of enterprise leaders, a lot of even businesses that are consumer facing, because one thing that determines success when you're in the Gen AI application space is not one is time to market, but also your ability to iteratively develop on your product. A very good example of this would be the likes of ChatGPT. That's the poster child, right? One of the key ingredient they're using for innovation is iterative deployment, development as well. So when you start to take this top of mind consideration, iterative development, developer productivity, you start to realize that you want to focus more time on what matters, which is shipping features and actually building the application. And we find out a lot of developers would rather not focus too much or even at all on the fact that they have to go through a bunch of database configuration to optimize it. And this is a phenomenon that I see and I call Postgres Regress, which is some developers are building, or some AI engineers or AI stack engineers or AI product engineers are building these tools and using databases that are not essentially optimized for AI workloads. Not saying they're not good for other use cases, but when you come to AI workloads, there are certain key criteria. So you go into this Postgres Regress when you sign up to be an AI engineer, and now you have to become a database administrator because now you have to start tweaking configuration to get a good bang for your buck from your database. That doesn't happen with MongoDB. With MongoDB out of the box, without any tweaking in parameters, you get that scalability factor, that ability that allows you to be very productive, very productive. So the key thing is role dilution, right? We all want to do the things we love and don't want to do any adjacent or any different tasks, become database administrator. And no offense to database administrators, we need them in different areas. But when I'm looking at AI engineers that are building this product, and when AI moves at the speed of innovation, your ability to ship and iteratively develop your application is a competitive advantage. On that note, I'll be looking at the comment section, and we're gonna be. I'll feel free to answer any questions. Feel free to ask any questions, and I will answer them. Don't answer the questions, or if you can, answer some questions. So we're gonna take things from the top. I'm gonna take you through this notebook, and I'm gonna provide a link where you can access this notebook as well. And I'm gonna this link is gonna be shared in a minute, and you'll be able to go into this notebook and test it, download it yourself, and see how see how you could tweak some of the parameters. So let's start from the top. The vector-based comparison for AI workloads, we've touched that. We're going to be looking at Postgres with PG Vector and MongoDB Atlas Vector Search. We're going to be running MongoDB locally. All the instructions for installing Postgres and installing MongoDB on your local machine are within this notebook with links to all the resources that will help you guide you through this notebook. I've tried my best to optimize and make both of the scenarios very similar for both of the tests. So, but if again, this is in a public repository, so you can always raise a PR for any improvements that could be made. I'm going to touch on a few things about the system. So all of this is my system configuration. We're using some database management tools. So we're using pgadmin. I'm using pgadmin. I'm also using MongoDB Compass. I kept the versions I'm using. We're using a single node deployment of each of these databases. And we're using Postgres 5.4. And we're using, on the MongoDB side, we're using MongoDB 8.0.1. And I've kept some information on the vector index algorithm that both of these databases are going to use to conduct vector search. So we're using the hierarchical navigable small word. That word is always hard to say for me. HNSW. So I've kept some information at the bottom in terms of all these algorithms that we're using. But one thing is there are some default configuration that comes with Postgres and PG Vector for tuning this HNSW algorithm. Again, really, we've noticed that the fact that a lot of developers want to stay productive, we've essentially configured the best configuration on our backend that enables most of these workloads to be handled without you having to tune some of these parameters. I've kept definition of these parameters below, and we're going to be using cosine similarity as our distance measure between vectors for both of these databases. And there's other information into the environment. Let me talk about the data set as well. We're using 100,000 data points, and they have allocated embeddings. And the precision of the data type of this embeddings is float 32. And each embedding has a dimension of 768 generated by Cohere. There's a link to the data set. It has 35 million. You can increase it within this notebook. This part explains the key metrics that we're looking at. We're looking at the operation for insertion or ingestion, and we're looking at retrieval, key areas that are really top of mind for developers building Gen AI products. And also feel free to say where you're tuning in from and watching in from and ask questions as well. In terms of the test that we're going to be conducting, I've kept it an example, but really I've explained it in the diagram of how we're testing things. But what we're going to do is try to mimic what we see when you go to production, or you have an MVP that is being used by a couple amount of users. And what you're going to get is a bunch of several applications making queries to your database. And that's what we're trying to mirror in this concurrent queries attribute variable here. And we're going to be we're going to be actually querying the database with 100 query for each of this concurrent query. So in total, we run 100 iteration, which is 100 queries, and then we have 10 concurrent queries. So in each experiment, we could have for 10 queries, for 10 concurrent queries, we can have 1,000 queries being asked to the database, which is a lot. And then we measure the latency for each of the query, and then we get an average to get our scores. All of this is in code for both the Postgres setup and the MongoDB setup, and I've tried to keep even the steps that you're going to be taking very, very similar and the same. So 7 steps for Postgres, 7 steps for MongoDB. And I show an example of just doing a very basic semantic search with both of these databases, which you can then extend to implement recommendation engines or RAG pipelines, but basic semantic search use case for both of this database. Another thing I would love to talk on is the data set. So we are using Cohere. You are going to need to get a Cohere API key, not to embed the 100,000 data points, but to embed the queries that we're going to be using. So I'm gonna explain this very quickly, but we've done this several times. But we're using the embed multilingual version 2.0, which is what the embeddings within the data set was created with. So we have to match that data set. The precision type is float 32, and then we extract this function will return a vector embedding for us, matching a sentence that we've inputted into the function. And these are the sentences we're going to input into the function. So you're not going to run, this is not going to be costly. This is just very straightforward queries, and they are the documents that corresponds to these queries are at the top of the data set. So it's really not going to be we're not going to extend the query because that'll be a lot of it'll be costly to generate that many embeddings, and it'll be time consuming. So once you generate this embedding, what I'm doing here is I'm actually storing it within a variable, and using the embeddings for this for these queries, using it as as the query vectors, so I don't have to keep re-embedding every time for each of the queries. Because again, if we're just looking at 10 queries if we're looking at 100 queries per thread, that would be 100 embeddings we have to generate, which is way too much. So we store the embeddings and then we just utilize them within the functions further downstream. So I'm going to take a drink of water. Please ask your questions. We got people from Brazil, people from Germany, people from India, and people from Toronto, Canada. I'm tuning in from London, UK, where it gets dark very quickly here nowadays, winter time. Okay, let's go back to this. So I'm going to touch on a few things, and I really want to leave some areas for questions as well, and discussion. So we're going to store this query embeddings, and I it's displayed in this notebook how they look. But then in this notebook, you get information on how you can do semantic search with Postgres using PG Vector. You get some information how you can do semantic search using MongoDB, and MongoDB access via Atlas CLI. So we talk about the data points here, and this is important actually. And I'm going to go up because I skipped a step in terms of the data setup, just to make sure. Yes, right here, I skipped this step. And this is an important aspect of this whole benchmark, which is we are creating our own JSON data from the data points in a data set. And the reason why we're using JSON is because when you actually go for AI workload, JSON is a common data format used to transmit data through the AI stack. So from your inference model to your LLM abstraction framework to your database to your application layer, JSON is usually the common format for data exchange. So we're going to be using JSON data, and we're going to construct a JSON data using the data point, the attributes within our data set. So the title, the text, the URL. I also remove a bunch of other data points that we don't need, like the ID, wiki ID, paragraph ID. We don't need this data point, so I just removed it, and I rename the embedding column from the original data set from emb to embedding. It just makes embedding makes more sense. So this is what the data set looks like. This is our data set. There's 100,000 data points, and then I've already explained the embedding generation and why we're generating the embedding. The key thing is you're not generating embeddings for the 100,000 data points. They already come with embeddings. You're generating embeddings for the queries that we have over here. Okay, so I'm going to touch on the Postgres setup, just to mention a few things that I'm using. So I've mentioned the libraries I'm using, pgvector. I also kept the versions of the libraries I'm using. I believe this is the latest one of pgvector. Also, where in this step right here, we are actually going to be storing our JSON data using the JSONB format available in Postgres. So what that is just what happens, you get the Python representation or the dictionary representation of your data, or JSON, which is then serialized and converted into a JSON string that could be handled within Postgres as binary data format. That's JSONB. You can use JSON as well, which is another data type within Postgres. I'm using JSONB because MongoDB, we store data fundamentally using the BSON data format, which is also binary JSON as well. So to keep things the same. And this, for most Postgres folks, would be very familiar, where we're creating a table and then we're creating our index. I'm going to touch on a few things. You have to specify your embedding vector size 768, and also specifying, this is where PG vector comes in, right? It allows you to have that vector data type. The extension allows you to have that vector data type within Postgres. Then you have the JSONB data type for your JSON data, and then we set the operation we're going to use, which is going to be the cosine, which is going to be our similarity, our distance function, and we're going to be calculating the cosine similarity by taking 1 minus the value of the similarity, the similarity value from each of the data points. So there's a few parameters here, which I believe I've explained at the top what each of the parameters, not all of it is mentioned here, but just to take it from the top, right? So first, we're using the hierarchical navigable small word. Such a hard word to say. HNSW. So this is a vector index algorithm that creates a graphical structure, which where you essentially have all the vectors of your node that are in different layers, and the M over here represents the edges per node in the graph. So this is the nearest neighbor of each node. So which one are they similar to? These are the edges. Then we have the EF construction, which is factor construction, set to 64. This is the default settings on Postgres. So these are not changed. Postgres or PG Vector, these are not changed. So this is, and you can tune this any way you want. Most folks probably won't, because I think the default settings are good enough. So we also have the exploration factor search. This is the number of candidates, well, the number of data points we want to consider for each node when we're searching. And 64 is the exploration factor construction is the number of edges we actually want to have each node to connect to during the index construction phase. So those are the key variables over here. There's some questions coming in. Uh, Rachel Nalake, that's so Nigerian. Excellent. Yeah, I am Nigerian. So let's get to this. I've seen someone asking a question, and I'll get to that as well. Keep asking questions. It's going to be very good. And also, the link to this notebook is on the chat as well, so you can follow along and maybe even run this as well if you're quick enough. Maybe you actually have local deployments of both databases, so you can run this notebook. So, okay, so we create our Postgres table, fun stuff. Then we insert data. So this is the insertion process. You remember that graph, that cool graph we saw earlier? For people just joining, we are going to be going back and looking at that. So we insert data into Postgres, and it's really the one thing when I was actually doing this, I realized is we have to serialize data that are not that are in JSON, or I guess in Python it will be a dictionary, which is a JSON-like formatted data structure. So we have to serialize data, which can add to that overhead when you're doing the insertion time. Also, and that's the only thing to take note of for this insertion. So what we're doing is we're measuring the time when we come into the function. Then we're looking at the end time once we complete the ingestion. And I did look at different. There are different ways you can do a batch insertion in Postgres. And I saw four different ways you can do a batch insertion, and I think this was the one of the optimal way, but I'm sure there are other ways that some Postgres developers can bring to light. Again, I'm a most people that I work with are AI developers, and we love to be spoiled for choice, but not too much choice. So we have this function execute menu, which I believe is a performance version of inserting batch data into Postgres. So and then we measure the time. I've commented out some print statement because for each this can get extensive within a notebook. So you can uncomment this if you want to see some individual data point or query execution data point when you're actually running the benchmarks. But it can get a bit annoying in a notebook because it's quite extensive. So that is the insertion function, and it all comes together over here when we insert. This is just an example of just doing RAG. You insert your data, you create your table, and you insert your data, and you have some metrics over here for that specific insertion. 100 data points inserted into Postgres. Next, this is a very simple semantic search, and it's using vector search to conduct similarity between a query vector and some vector embeddings we have in our database. That is just a general way of how vector search works, and we're using this signifies the utilization of cosine similarity, and then we return the value and order them by similarity, and then we can see when we ask the query when was YouTube officially launched and by whom, we get the results and we get our similarity score. Very interesting, right? So we could take the same step, again, defined with MongoDB. So I'm just going to highlight some key things, then we'll go back to that diagram. So for people that just joined us late, you're going to get to see what this benchmark results. And for those who can't wait, go to the GitHub link and you can scroll down and have a look at the results. So we're going to install MongoDB using Atlas CLI. What is Atlas CLI? Well, what you get with Atlas CLI is a command line interface that allow you to create local deployments of MongoDB database and also connect to your MongoDB Atlas. So you can experiment with your local deployment and then deploy your database over to MongoDB Atlas and also connect to your MongoDB Atlas cluster as well with the Atlas CLI. There is more information in all the links I've provided, and I've also specified how Atlas CLI was installed. Okay, on that note, to get things started, you're going to have your connection string. I'm going to increase this. Yes, that feels better. Yeah, so you get your connection string, and then you put your connection string in your environment. And then one thing we're doing here is we're just going to use PyMongo to actually access our client, which is a connection to our database. And what we're going to do is extract, create our database, a collection name, and then we can create our collection. And this sets it up ready to ingest data. I usually do this because I run this experiment several times so we can delete all the stuff in the database to make it clean. And then we have our vector index creation. So vector index explained is a data structure that allows for the efficient retrieval of vector data or vector embeddings. So what the steps is doing is just creating a vector index within MongoDB. So a vector index within, and this is something to point out, defining things within MongoDB is very familiar, right? So defining your vector index is you're doing it using that JSON structure that we're familiar with. Remember when I said we have that basically the language of the AI stack, because it's how data is transmitted through all the components within the AI stack used by all your providers of any of the technology providers within the stack. We're using that within MongoDB because it's familiar to developers. And what we do is we're creating our index. It's going to be a vector type index, specify the path. we specify the number of dimension, which is 768, and the distance function we're going to use, which is cosine. So nothing new or different to what we did over in Postgres. Typical steps. Next, we're gonna similar as well our insert function, but you notice there is less code just visually because inserting data into MongoDB, because we have that JSON foundation for storing data types in MongoDB, it's easy to install JSON-like or ingest, sorry, not install, ingest JSON-like data within to MongoDB without any serialization. So what do I mean by serialization? You have data in a format and you need to change it, transform it to another format. Now, this is all well and good if you're dealing with maybe one or two queries. Now, if you have an AI workload that needs to operate at scale, that operation of changing that data point from one format to another becomes an overhead. And then you start going into the realm of real-time or near real-time AI application, it becomes a bottleneck. And then you have to start looking for optimization strategies. And then you become, no offense to database admins, you become a database admin. But you want to be an AI engineer. You want to make Gen AI applications that have real impact. So again, we record the time at the start of the function and we collect all the key benchmarks and all the key attributes that we're interested in. And inserting documents into data, though it's very simple, and we just run the function to actually insert it. Okay, and there we go, all done. And now we move on to that semantic search function. I've actually just seen something. So I'm going to take a note for myself. I just remembered something that I'm going to update on this notebook. It's going to be useful to a few folks, because what I'm looking at is I'm going through my code and obviously I'm writing this and it looks like I am converting the data frames twice, which is interesting. But nonetheless, which is fine. Actually, no, I'm not passing it into the function. So this is fine. We can ignore this line. That's excellent. So we're just going to do the conversion once. Okay, so let's get back to this. I print out the results of the insertion. Again, this is just for visualization. You can remove this line. And then we have the same process, right? We have semantic search and we're doing it with MongoDB. Here we have our query embedding. We're not going to regenerate the embedding. That'll be very costly. We're just going to pick one from what we had in our embedding dictionary. This one contains all the embedding. So for the user query that we pass in, we get the corresponding embedding in that dictionary. And then we can conduct our vector search operation. And I want to point out one thing here, which is a lot of people, and I've made the point up here, and this is a lot of people might be having to build AI applications are coming from data science background, machine learning background, or data engineering background. And now you have to become an AI engineer, or at least work with AI engineer. There is a notion of a concept of pipelines within this fields or within this roles. And what that means is you have a series of operations. Operations can also be executed in parallel, but you have a series of operations that execute consecutively after each other, where the output of one operation is the input to another. So that's what a pipeline is, and you have processes within a pipeline. A common concept within a lot of fields. With MongoDB, we bring that mindset into when you're constructing your query. So you can imagine, I'm going to work backwards. So we have the aggregate framework where you can actually specify a pipeline where we have a vector search stage. And what that's going to do is going to get a bunch of documents that correspond to the query vector. Then we have a project stage. We're going to remove the embedding. This is an additional, we're just going to remove the embedding because we don't need it further downstream. We did the same for Postgres. We're not returning the embedding as well. So, and we also add the vector search score. So we saw the score for the Postgres. We're going to see the score for the MongoDB. Now we have the same query, and we get actually, if you notice, similar results. The top one is where the answer is. Then we're requesting for 5 documents in both of the database, and then we get the results. Those of you who are very watchful, you see that the similarity score are different between the databases, because the engines behind these databases that conduct vector search implement the HNSW and also the cosine similarity score calculation maybe a little bit differently. But that's why you see the difference there. Just wanted to explain that in case it's something that sticks out to a few of you folks looking at this notebook. So we're getting closer to where we will see the results. And I'm sure some of you already gone into the notebook and I've seen the results already. But we do the same process. The first thing is we're going to insert, this is the part 4 is the vector database benchmarking. And this is the insertion process, the ingestion process. I'm just going to look at the results very quickly. I've explained how we're inserting the data. We're essentially starting with 1, then doubling all the way through until we've finished or exhausted our data points. So just to focus on the results, then I can go into some areas I want to highlight. Again, any questions you have, any questions, feel free to ask on the chat. And let's go into the insertion benchmark. I'm just looking for the graph. Yeah, so, okay, here we go. Do I have to zoom in? It's quite weird. Zooming in is zooming out. So, again, I was talking about the things that really matter to AI developers, AI engineers, AI stack engineers, wherever you want to call yourself. If you're building Gen AI applications, these are the things that matter. Ingestion time, latency, obviously cost as well, but we're not using any cloud deployments for both of this. This is on our local environment. That's another talking point that should be top of mind. And again, there are ways that MongoDB Atlas enables operational efficiency of AI workloads. So quantization, and we have a lot of knowledge around how to optimize retrieval and even other processes post retrieval. So a lot of that is in our Gen AI showcase, and we have courses on that on the internet. But going back to what is top of mind for developers, insertion time. How quickly can I get my data into my database? It's important because when you're running all your automated process and you're running at near real time and you're trying to enrich your vector database with real-time knowledge so you can give your users the key information that makes them valuable or more productive. This is why this is top of mind. So how quickly can that pipeline be optimized, right? How quickly can that pipeline be executed? And also, you're thinking about scale, right? It might be great for one, if you only have one user making one query per day on your application, okay, you can use any database. But when you're thinking about scale, you're thinking of AI workload, you're thinking about the future, you're thinking about, okay, do I want to go through the role of through the phenomenon of Postgres regress and row dilution, or do I want to be a productive developer, which is making Gen AI applications, making AI applications that provide value? These are things you should be considering. One thing I want to point out is the amount of rows you can ingest in this single node deployments of each of these databases per second. So with Postgres, you can ingest 652 rows, and with MongoDB, you can ingest 2,700 plus rows. So you can imagine how quickly you can get through a bunch of data points. And again, this is just on my measly old machine, which I've kept the configuration at the top of this notebook, because when you start looking at the cloud and you're looking at MongoDB Atlas, things can get much faster. They're much more optimized, and horizontal scalability, vertical scalability and horizontal scalability are available at the click of the button. And talking about MongoDB Atlas is a different topic, but the user interface is very intuitive for ensuring developer productivity is maintained throughout the entire process of working with MongoDB. But here we can see this part where different batch sizes, right, where different sizes of data, and MongoDB remains performant. That's the key thing for AI workload, right? We're going all the way up to 40,000. And you can play with the numbers at the top and ingest more data from the Cohere data set and then run it, see the performance for yourself as well. Next, this is how we're actually running our benchmark. We're going to do a benchmark of the semantic search or the retrieval process on both of the database, Postgres. But the key thing here I want to point out is, and I'm going to zoom in here, is how we're running this. So we have a bunch of query, and we choose for each time we want to run a query, we're going to choose a random choice. So you can change this to make it static, you still get the same result. I just made it random. So both random for Postgres and random for MongoDB as well. We're keeping the same conditions the same. So we actually get our query, we choose our query, we record the start time, and we conduct semantic search with the query, and we're only going to retrieve 5 documents. Again, you increase this number, you're obviously going to have to spend more time looking for results that match your limit, or at least the number of documents you want returned, and that can increase the latency both for both databases. But we have this defined in this function, execute single query, and then we create threads for the number of queries we want to execute. So, and then for each of this thread, we're measuring the start time and the end time for the query to return. Then we take an average to get the average latency, and we calculate the throughput, which gives us the amount of queries per second we're processing. So this is how the function works for both MongoDB and Postgres. It's exciting stuff. And if you could look for ways to optimize it or things that we should be looking at, yeah, bring it up, raise a PR. So this is the same. I've touched on this before. We make a connection to our Postgres database, and then we run our benchmark. We do the exact same thing, the exact same process. I'm sure there's I could have moved this into a global variable, so I'd have to redefine it. Anyway, we do the same process, right? Random choice for MongoDB. Then we search with MongoDB. Then we're creating all of this threads, and then we're measuring the latencies as well and taking the average. And then we plot them against each other. We visualize it, and this is all the visualization code. But very quickly, the 3 data points, I'm scrolling too quickly, I'll slow down. The 3 data points are the latency, the throughput, and the P95 latency. The average latency is, on average, how quickly was I able to get the results for each of the concurrent queries. The throughput is how many queries can I actually put into the database per second. And then for P95 latency is for how quickly do I get the results of 95% of my queries back. So here you go. I've touched on this at the beginning. For those of you joining, you get the pleasure of hearing me speak about it again. So we're going to be talking about latency, and I keep talking about latency because that's going to be one of the key words you're all going to be hearing in 2025. I think the patience of the consumer is wearing out, where at least for chat interface, I don't want to be waiting for about a minute for any response from any chat interface, except you're using some crazy advanced reasoning model, I think, or one doesn't even take up to a minute for reasoning. But one thing that should be top of mind all the way from the POC stage, or even the idea stage, is just latency, because the form factor of these AI applications are very, very quickly change. They change very quickly. 1 minute we're talking about RAG, now we're talking about agentic systems where we have to conduct several operations to achieve an objective and want to make sure we're getting the response to the user as quickly as possible. Then we're going to go into this conversational AI interface era next year, or is already here, where the time to actually get the results, the time to hear the vocal feedback is very important for interaction and engagement with your AI product. And you can go into Sora or video generation. Right now, Sora takes a while to generate some video. The higher the resolution you go. But believe me, latency is top of mind for them, and latency should be top of mind for most AI developers. That's why I'm focusing on latency. So we have this idea that we need our applications to be faster at the POC level, and we don't even want you to think about it. We want it to just be a given, right? We don't want you to configure your database to make it faster. This is just how it comes out of the box. We have someone from Ethiopia. That is most of my friends are from Ethiopia. That's a very, very nice country. So we're going to talk about throughput. How many queries can we actually process in a second? And again, MongoDB remains performant in latency, which is a key thing when you're scaling. Another key thing remains performant in terms of throughput. How many queries can I process per second? And here we can see we can process. I showed the average earlier on, but here we are processing for 96 concurrent queries. We can process around 1,000 queries per second. And now we have the P95 latency, which is how quickly can I get the 95% of my queries? How quickly can I get them back? And of course, we see this spike here because I am not running this on a clean environment. I don't know if that's a thing, a clean cloud or virtual environment. But you could run this yourself, or you could take this and put it on an environment and see the results for yourself. The key thing here to take away is, and I put some extra note, is there are several reasons why MongoDB, and we're not saying, or I'm not saying, don't use Postgres. Postgres has existed for a very long time. A lot of applications are built using Postgres. But when we're moving into a future where, or the future is here now, to be honest, where you're moving into a future where a lot of the considerations are latency, operational cost, you're thinking about data interchange formats. And what I mean by that is, even from the model providers, we see them bringing out structured outputs that is in JSON-like format. You need to start realizing that serialization and converting data from one form to another within your stack is an operational overhead. And you can remove that when you're using optimized databases for JSON-like data like MongoDB, and prevents you from, again, no offense to database admins, prevents you from becoming a database admin. And if you want to become a database admin, there are parameters you can tune as well. So I think I've reached to the end of this notebook and discussions around this topic. There's a lot of ways we can go in this, and there are a lot of experiments that we can talk about this. So I did it. All right. If there's some topics that you want me to talk about, just put it there and we will talk about this. So and I could beat this drum, but one thing I'm very, very, very that I take that is very important for me is making sure developers like yourself are successful when you're building this application. I build applications myself, and very quickly getting something that works out of the box and you can optimize, but you don't have to think about the optimization of it as a whole role. It is time saving, and it really, really makes developing this application fun. For me, it makes it very fun. So there are a few things that we can touch on. We're coming up to the hour. I think I've got some few questions. Let's see. I'll go to the top, and you can keep asking questions as we're going through this. So we have the link to the GitHub repository, which is fun. And if you're there, fork the repository as well, and get a bunch of resources as well from there. We have agentic use cases, RAG use cases, evaluation use cases, anything you can think about. And if you want anything, just ping us, and we will try to address all the use case or stack composition, or the stack composition for you. So why do we need Postgres or MongoDB? We can use Apache Peanuts, which runs query with very low latency. You know what, Kuno, my knowledge on that is very limited, but I will note that down and I will message you personally and we can discuss on that. Or you can message me on LinkedIn with the questions and we can start a conversation around it, right? And yes, the end goal is to get the data with very low latency, but we also have to think about horizontal scalability, vertical scalability, sharding. We have to think about availability as well. And there's so many factors, but this is just the basic, right? The fundamental, which is I'm an AI developer. I want to find a database for my AI workload. What should I be thinking about, right? I'm not telling you what to choose. I'm trying to tell you what to think about. Because when you know what to think about, sometimes the choice becomes very obvious, right? So I speak to a lot of people that want to do graph RAG. and you're using another database, another specialized database. Or you could just use one general purpose database optimized for AI workloads, which is MongoDB, because you can do graph RAG in MongoDB. You can do all the RAGs in MongoDB. Um, I've said RAG a lot of times this year. Yeah, so yeah, and we see, yeah, I'm always glad to see another Nigerian on the chat. So yeah, I'm Nigerian, based in the UK. So it's correct that it's not supported in Community Edition. This is only going to work in Atlas. That is quite an important thing to point out. Well, right now I'm running MongoDB on my local instance, so you can actually run this locally. But yes, we at some point we are going to be releasing all the features on the Community Edition as well. Is the framework more or less like LangChain? Give a brief overview. What framework? I am not using any framework in this um, demonstration. But is it more or less like LangChain? Let me help. LangChain is an abstraction framework, and what it does is it removes some of the code you have to write to achieve some results with maybe your database or your prompting, and that's what they do as well. So LangChain, Llama Index, Haystack, they are abstraction framework, and they abstract the complexity of implementing some of this or building some of this application. So nothing here in this example is like LangChain, but one of the key themes that you need to take into consideration is developer productivity. And every player in the stack that really cares about the developer like we do is really focused on making developers productive and getting them to the finish line as quickly as possible. So maybe in that sense, we all have the same, we have similar missions. It's coming to Community Edition very soon. Um, okay, good to know. For me, that is a must to include all type of project. Cost, yeah. Think about customers, use cases, pain points of your customers as well. Is very important to know. But the key thing is, this is what I want you to take away. Postgres is good and has been used for a very long time. When you're entering the era of AI or looking at building AI application, MongoDB is optimized for AI workloads. And I've shown you the different items you should be thinking about. I'm not showing you all of the items you should be thinking about. We'll be here for hours, but I've shown you some of the things you should be thinking about. Another thing, since everyone is an AI expert now, we like to do a lot of experimentation in machine learning and data science. But one thing is, I don't want, and we don't want developers to experiment with databases. We want you to experiment with your techniques, not your databases, because that will definitely go against the thesis of developer productivity that we're focused on. And hello from Chicago. Hi there from London. Um, So could you confirm if the MongoDB vector search work in MongoDB Enterprise version? I would take that down, or you could ping me the question on my LinkedIn, and I can get you that answer. But for now, you can use this notebook and just have a local deployment instance of Atlas on your machine and experiment away. Okay, I think we are just at the hour, and I see no questions coming through. And this is going to be my last live stream for the year. And it's been a crazy year. We went from RAG to agentic systems / compound systems. We did a lot of YouTube videos and making you guys very successful with MongoDB. And we're not going to stop in 2025 because we're really going to go faster. We're going to bring you good content, and maybe we do more database comparison for